I'm going to talk to you about the digital currency Bitcoin. In this presentation, I will refer to Bitcoin in two ways. First, there is Bitcoin the unit. As a unit, you can think of one Bitcoin as something similar to $1. Second, you have Bitcoin the system. The Bitcoin system is the underlying mechanism that defines how Bitcoin actually works. Bitcoin is growing really quickly, and it has the potential to change the way all of us use money. Here are some of the companies and groups that already accept Bitcoin. They include Overstock, the rapper 50 Cent, the Sacramento Kings, and many more. This presentation has two parts. First, I'm going to describe what Bitcoin is and why it's special by walking through three of its defining features. Second, I'm going to explain how Bitcoin actually works. Rather than explain the entire system as it currently exists, I'm going to work with you to build our own implementation of Bitcoin from scratch. By recreating Bitcoin in this presentation, we will learn why Bitcoin is structured the way it is today. Alright, let's begin. Bitcoin is often described as a digital currency, but we already have digital currencies. Most banks allow for online transactions, and PayPal has been around for over a decade now. What makes Bitcoin special? Here are three of Bitcoin's defining features. First, Bitcoin allows for instantaneous transactions with anyone in the world for fractions of a penny. Before Bitcoin, if I wanted to send money to someone, I would need a bank account, the other person would need a bank account, and one of us would have to pay a significant transaction fee. If I wanted to send a large amount of money, or if one of us was in a part of the world with an unstable currency, the transaction would take much longer, and the fee would be much larger. With Bitcoin, I can send money to anyone in the world instantaneously for fractions of a penny, and all I need is a piece of software and an internet connection. Second, Bitcoin introduces genuine scarcity into the digital realm. Unlike physical goods like gold, digital resources are not inherently limited in their supply. Many attempts have been made to enforce a limited supply of digital resources. iTunes is one attempt that has largely failed. Given past failures, it is incredible that Bitcoin has succeeded in limiting the supply of a digital resource without a central authority. Finally, Bitcoin prevents fraud and theft without a central planner. Currently, we have to trust central banks with the integrity of our currencies. These systems are inherently trust-based. If the Federal Reserve Chairman makes a bad decision, we all have to face the consequences. Bitcoin is trustless, and that means that the rules encoded in the software are enforced without trust in anyone, let alone a central organization. Now let's talk about how Bitcoin works. As I mentioned before, we're going to recreate Bitcoin from scratch. It's very important that our version of Bitcoin, like the actual version, has the three defining features I just explained. Our initial implementation will have many flaws, but by improving on that first implementation, we will gain a deeper understanding of why Bitcoin is structured the way it is today. Here's version 1. In this version, if Alice wants to send a Bitcoin to Bob, she should write and sign this message. I, Alice, am giving Bob 1 Bitcoin. In Bitcoin, each of these messages represents a transaction. By making Alice sign each transaction, we're solving a problem. Alice's signature ensures that she can't turn around and deny sending the Bitcoin. Next, Alice should send the transaction to everyone running the Bitcoin software. Now everyone knows that Bob has 1 more Bitcoin and Alice has 1 less. This first version has one major flaw. Alice could keep sending the same transaction 5 times. What would that mean? Does Bob now have 5 different Bitcoins, or 5 duplicates of the same Bitcoin? This is a problem version 2 needs to solve. In version 2, we're going to solve that problem of double spending by introducing serial numbers to make Bitcoins uniquely identifiable. Now, if Alice wants to send a Bitcoin to Bob, she should send the message, I, Alice, am giving Bob 1 Bitcoin, with serial number 8732. This way, Alice can only spend each Bitcoin once. There is a problem. Where would these serial numbers come from? And how do we manage who owns which Bitcoin? With serial numbers, Bob can make sure that Alice doesn't send him the same Bitcoin twice, but how can he be sure that the Bitcoin belonged to her in the first place? To make version 2 work, there needs to be a trusted source of serial numbers. The traditional source is a bank. This bank would provide serial numbers for Bitcoins, keep track of who owns which Bitcoins, and verify that transactions are legitimate. Now when Alice sends her transaction to Bob, he can check with the bank that the Bitcoin actually belonged to her and that it is unique. There is a problem. Version 2 did solve the issue of duplication, but it lost the decentralized nature of version 1, where transactions were announced to everyone, without a bank. Version 3 should bring that decentralized structure back. In version 3, we're going to bring back that decentralized structure by making everyone the bank. Now everyone has a complete record of all Bitcoin transactions. We'll call this record the blockchain, since that's what it's called in the Bitcoin software. Now when Alice sends her transaction to Bob, he can check his copy of the blockchain to be sure that the Bitcoin actually belonged to Alice. If that works out, Bob announces the transaction to the world, and everyone updates their copy of the blockchain. There is a problem. What if Alice sends her transaction to Bob and Charlie simultaneously? Both will find that the Bitcoin belonged to Alice, accept the transaction, and announce it to the world. How should other people update their copies of the blockchain? Obviously, both Bob and Charlie can't own the same Bitcoin, so we have a problem. Version 4 should solve that. We can begin to solve that problem of double spending in version 4 by giving everyone the power to verify a transaction. Now when Alice sends her transaction to Bob, Bob shouldn't try to verify the transaction alone. Rather, he should broadcast the possible transaction to the entire network of Bitcoin users and ask them to help verify it. If enough users verify the transaction, Bob can accept the Bitcoin and everyone will update their blockchain. This way, if Alice tries to double spend on Bob and Charlie, other Bitcoin users will notice and reject the transactions. There's a problem with this approach. Alice could double spend on Bob and Charlie by taking over the Bitcoin network. If Alice is clever, she can use an automated system to set up a large number of separate identities that overwhelm the Bitcoin network. Now when Bob and Charlie ask the network to verify their transactions, Alice's many identities swamp the network and announce to both Bob and Charlie that the transactions are fine, fooling them into accepting the same Bitcoin. Version 5 really needs to solve this issue of double spending once and for all. We can solve the issue of double spending in version 5 by implementing something called proof of work. In a proof of work system, when Alice wants to give Bob some Bitcoin, she announces her transaction as a message to the entire network. As other users receive Alice's transaction message, they add it to a list of pending transactions they've been told about, but haven't yet been verified by the network. For instance, another user named David might have this list of pending transactions. If David wants to verify these pending transactions in a proof of work system, he has to do 3 things. First, David has to check his copy of the blockchain to make sure the transactions are legitimate. Second, his computer has to use resources to solve a hard mathematical puzzle. And third, he has to announce the block of transactions to the network. Before we take a closer look, remember that if David doesn't want to verify any transactions, he doesn't have to. He can just let other users do that. You might be wondering, why does David's computer have to solve a math puzzle? This is an important question. By requiring David's computer to solve a math puzzle, we are actually solving the problem of double spending. Let's take a look at that problem again. By setting up a large number of separate identities on the Bitcoin network, Alice can double spend on Bob and Charlie. We want to make it costly for Alice to double spend, but it's difficult to identify dishonest actors before they act, so we will simply make it costly for anyone to verify transactions. In the Bitcoin system, that cost is called proof of work, and it involves a math puzzle. You can think of proof of work as a competition to verify transactions. If your computer solves the math puzzle before the other computers on the network, you will verify the pending transactions and receive some Bitcoin as a reward. Proof of work prevents bad people like Alice from double spending because it puts them in competition with everyone else trying to verify transactions. So long as most of the computing power on the network is controlled by honest people, bad people like Alice will have a hard time doing dishonest things, like double spending. And that's it. We've recreated Bitcoin. Here's a table of the versions we went through, their most important features, and the value they brought to the final system. Hopefully now you have a better idea of how Bitcoin works and why it's so special. Thanks for watching.